Okay, it's a great pleasure to have Vivek. Everyone knows Vivek. I think most of you know Vivek. Here, Vivek Datar is been a Raja Ramana Fellow at IMSC for the last 3 years. And this month his term is coming to an end, in celebration of which he is giving this 3 lecture mini series of talks. So it's unfortunate that because of COVID he could not actually move here lock, stock, and barrel, but I think we've all enjoyed whenever he comes and he talks on various aspects of physics. So we are all looking forward to this mini series as well.
Thanks, Induvati. So this, I should give a slight background to this these talks. Murthy had organized a workshop in the Vizianagaram college called Maharaja's College, and so all the three academies they fund such ventures, and so Mallesh, Murthy, and myself we gave talks. Mallesh and of course Murthy gave theoretical talks, and I gave things connected with experiments, which illustrate some of the topics that they talked about. When I mentioned this to my Van de Graaff colleagues, they said, "Why don't you give this same set of talks here as well?" So I was a little apprehensive. I said, guys are all practicing nuclear physicists. No, I said, so you please give these. So that's the background. So, and of course, 2 days back, my laptop display died. So, you see this, first of all, lecture 1 at Van de Graaff. So it's not at Van de Graaff, obviously. I could change that because changing from PowerPoint to this one, open office is a hell of a job. So anyway, I left it like that. So, anyway, this is the background. And so I'll just show a couple of slides which basically introduce what I was going to talk there, and part of which I will talk about here. So these lectures are meant to explore some of the phenomena which illustrate quantum mechanics. Some of it is such that quantum mechanics does better than classical mechanics. Some phenomena are purely quantum mechanical, so this cannot be understood within the classical framework. So these examples, for instance, are of the second type, purely quantum mechanical, photoelectric effect, Compton scattering, pair production, tunneling, double slit experiments in various forms. I will come to that probably in the third lecture. Okay. And then, of course, there are other phenomena like which I will not talk about at all: superconductivity, magnetism, lasers, semiconductors, whatnot. I mean, there's a whole set of, most of the things that we deal on a microscopic scale has to involve quantum mechanics in one way or the other. And then, of course, there are other things like black body radiation, charge particle scattering. Some of them, for instance, could be explained by classical mechanics, but quantum mechanics does better in some cases. It gives a deeper understanding. Okay, so the outline for that set of talks, which I had intended, was this. So I'll talk about the 3 topics here. Maybe at some later stage, there is enough positive feedback. Maybe I can talk about this some other time when I come next time. So I had started out, of course, with the 2-slit experiments, which involved electrons, photons, neutrons, but also molecules, big molecules. How big? Almost like 7,000-8,000 atomic mass unit molecules. They have been shown to interfere with each other. So then Bose-Einstein condensate have been shown to interfere. That's the scale at which we have gone to the 2-slit experiment. Then tunneling through the barrier, that's the topic of today. So there is a permutation done on the order of the lectures. That's how tunneling is today. So I'll talk about alpha decay, about sub-barrier fusion, but in between I will also talk about other kinds of decays, spontaneous decay, involving the tunneling. And some of them are really current in the sense that their experiments are still being done. And then there is this, the inverse of the spontaneous decay through tunneling, namely a reaction in which two composite particles, projectile and target, come together and undergo sub-barrier fusion below the Coulomb barrier. That also involves tunneling. Then I will talk about this in another lecture on the radioactive decay law. This is a very old law, which is almost like 120 years old. But there is a context to it being looked at more carefully, and I will discuss that at that time. So there are experimental tests Some of them, in fact, have been done to address this problem of short-time decay, which could have an impact on whether or not we should be finding proton decay at all. Because if the exponential decay law is not valid at short times, we shouldn't be seeing it anymore, irrespective of how short the lifetime is, 10 to the 29 years, 10 to the 32 years, whatever. And then these two, I'll talk at some later stage next time. Okay, so now I'll switch from this talk. Yeah.
Stop share.
Again, one more escape. So this is today's topic. Okay, so that's the first slide. So this is just a cartoon to which I found somewhere. You have this man looking on the other side of the wall, and then the lion is also trying to find out who's there on the other side. And of course, with classical mechanics, it's true. Of course, this guy cannot have anything to do with the man on the other side. But if H cross were, for instance, very large, then this guy would be able to tunnel through the wall, and then of course he has to run for his life. Okay, so some of the examples of quantum mechanics, quantum tunneling, which is basically that a particle penetrates a classically forbidden barrier. So it has an energy which is lower than the height of the barrier, and therefore it cannot reach there on the other side of the barrier. If to start with, it was on one side of the barrier. If everything is classical. Now it can do that through quantum tunneling and with a certain finite probability. And then this probability, of course, increases as you increase the energy, come closer to the barrier top, or the barrier somehow becomes thinner. Then, of course, also the probability will increase. The first time that this quantum tunneling concept was ever used was in the context of molecular spectra by Hund. That was in 1927. And this involved molecules going from being at the bottom of one well into another well. So there is a double well, and the electron makes a transition from one well to the other. That's what is involved. So this was used also, tunneling, used by Fowler, Oppenheimer, Nordheim, to explain field emission. So if you have the atom sitting in an electric field, then of course you have a potential which is going one way. So you have effectively a barrier which you can cross depending on how you can tune up the electric field strength, and you can have tunneling, and that leads to field emission. And they were able to explain. Interestingly, Oppenheimer did not have a single figure in his paper. Just mathematics. The other people had some figures to show how these things happen physically and so on. In 1928, Gamow used this theory in nuclear physics for the first time to explain alpha decay of nuclei. What is less well known, and in fact, even I was not aware of it till I read this article by Merzbacher in Physics Today, where Gurney and Condon had also looked at this same phenomena at a very similar time, independently of Gamow. Of course, Gamow talked about it a lot in some of the meetings and so on. He also went to Cavendish lab, and he was in fact instrumental in helping get funding for this small accelerator, Cockcroft-Walton accelerator. Rutherford was in a quandary because for those days it required a substantial sum of money to build that accelerator. There's a DC accelerator built basically on the principle of voltage multiplication. If you have an AC source, so you multiply it using a RC chain, and then you can go up to about 1,000,000 volts. Of course, in those days, they couldn't go up to 1,000,000, they could go up to a few hundred kilovolts, to 300 kilovolts. And so when Gamow came around to Cavendish lab, he said, look, I mean, this is exactly the inverse of alpha decay. So you have, instead of some particle decaying after tunneling, these people want to build an accelerator to look at the inverse process. So two particles are coming together and tunneling. Because the barrier for the reaction that they were looking at, they intended to look at the first reaction, proton plus lithium. And that barrier was already of the order of MeV or 2 MeV. So the energy that they could access using the Cockcroft-Walton is small. But quantum mechanical tunneling helps you get there. So, in fact, Gamow strongly supported such thing, and that's how Rutherford was found the funding that was necessary for Cockcroft-Walton. But they got the Nobel Prize much later. This was around the mid 27, 28, and they got the Nobel in the 1950s, early 50s. Okay, so then there are other examples.
Great. This is
Yeah.
fusion, the proton
Pardon?
lithium fusion.
Yeah, proton plus lithium, it fuses together. It goes to beryllium. Then that beryllium is unstable in the ground state itself. And so then that decays to 2 alpha. You have to just detect the alphas, and that's a sort of easy thing. The other examples of tunneling are in the Josephson effect, which is actually quite a rich source of physics and also applications. So you have basically a superconductor, two superconducting, let's say, conductors on either, which are separated by an insulator. And if that insulator is thin enough, the electrons, the Cooper pairs from one part of the superconductor can tunnel through this barrier and go to the other side. And in fact, there are DC and AC Josephson effects, and which are quite interesting. One of these also leads to the very accurate measurement of not just the fundamental constant, but also the magnetic field. Very small magnetic fields can be measured. And that's the so-called squid device. Okay, so these are examples. And then there, of course, there is a more current example of the tunneling electron microscopes. You have a probe, you have a voltage applied to it, and then you go close enough to a surface, and you can arrange such that the tunneling current, the electrons that come out from the substance onto the probe, you can arrange that that be constant. So then the piezo device actually moves it up and down, and so you can actually get a sense of the topology of its surface. So, for instance, people have mapped silicon single crystal, the ups and downs of silicon atoms in lattice. And this is a technique that is now very widely used. Not only do you do tunneling electron microscopy, people have also done tunneling electron spectroscopy, which is another advance of that. You also measure some other things about the electrons that come out. Okay, so this is just the background to what I will talk about. The word tunnel effect was first used by Schottky. This is the paper that refers to it. And then, of course, it became known as the tunnel effect in a textbook by Frenkel. So from the 30s, early 30s onward, this tunneling became a common, came to be of common use. So as I said, Hung first used the fact that these electrons tunnel. So for instance, if you have a double potential well in one dimension, then you have this, sorry. Oops. Press the wrong button. So you have this double well. You can have an asymmetric double well, or you can have a symmetric double well. And then you have energy states in these wells. So if you go deep enough, then these separations just correspond to the curvature of this well. And similarly here. But if you go up, then of course these states have to mix. You have to diagonalize the full Hamiltonian. And then these are the wave functions that correspond to electrons in the ground state here. So this has no node. This has one node and then two nodes. And then at this stage, since the excitation is high, you can also see this this second well also has an effect on the wave function, and so on. Go to higher and higher excited states, of course, both wells matter. Similarly, if you have a symmetric double well, then you have wave functions. The ground state is this, but actually it splits because you can symmetrize or anti-symmetrize the two wave functions. So you have this and this, and so on. And then you have excited states. So if you have motion in such a double well, then you can have a state, for instance, which has the amplitude with a certain phase. And then this can tunnel from one well to the other with a certain frequency. And that frequency can be compared with the oscillator frequency, because the oscillator frequency is the same for both these wells. And Hund showed that, for instance, the left-handed chiral isomers and the right-handed chiral isomers, they are connected by very, very slow transitions. So he said that if you have a left-handed isomer, it will remain. So the time scales are of the order of many orders of magnitude higher than the lifetime of the universe. So it will remain this is an interesting problem that he thought about. However, in other cases, such as, for instance, this ammonia, the two frequencies are of a similar order. And this leads to the fact that you can now excite these transitions in the microwave region. And in fact, you can do a resonant excitation as well. So this led to the development of the ammonia maser by Towns.
Sorry.
Yeah.
One that causes transition.
Yeah.
Is for the same like the double well.
Yeah, so let's go back to the states in that well. So you see, this is this doublet here. This is this doublet.
Yeah.
Okay. So you can excite these transitions. So when you make a state, when you have an excitation such that it makes a coherent state of both these, then you can have, it's just like our neutrino oscillation. As it develops in time, it goes from one to the other and swings back. And so this oscillation can be made use of to make a basis. So this transition frequency is in the region of. So happens.
In that case, if you put it in one, it stays there for a very long time. Tunneling lifetime is very long, right? For the left-handed isomer.
Yeah, so that is a different situation.
And that
Here-
situation I'm asking.
Yeah,
what
yeah.
is the
So
coupling
there, I think maybe the couplings might be even smaller.
Yeah.
In the case of ammonia, this is due to actually two configurations of ammonia. One is not top, below. And
But all
you have to symmetrize or anti-symmetrize the wave
all
function.
electrodynamics, right?
Yeah. There's nothing
Yeah.
in 1927, 28.
So 0, 1 are the, sorry,
Pardon?
they are very closely related.
Yeah.
One is the excited space.
That's right.
So I can't really see what's the tunneling there. So.
No, so the state has two components, 1 and 2. One corresponding to some electron in the first well, other in the second. And when you take because it depends now, you can put two phases to it, and they can in principle be slightly different depending on a small interaction that splits the energy. And that is what leads to this small split. So 0, 1.
He's asking how is it tunneling?
How it is done? No, so it's
You can lift one of the potential and gradually introduce it, and then you will see that the left-hand wave function will gradually reshape into this. So that is how tunneling affects the full wave function.
I mean, if it is, for instance, the tunneling part is if it were created completely in this one of the states in one of the wells, it would tunnel here. Now the actual thing, because these are you produce two states and they're very close by, so they are actually oscillating between these two states. And so at one point it will go completely to one well and at another. So it's actually tunneling between these two
Okay,
wells.
so you're saying.
That is the tunneling.
So you're saying 0 and 1, you created a wave packet which was
Yeah.
localized in
Yeah.
one part and this going
Yeah,
back and
and
forth.
that's right. And then how it goes then depends on the phase, and so that's. Okay, so this I already covered. So the next problem which Nordheim, Fowler, and Oppenheimer and so on attacked was this phenomenon of thermionic emission. So in thermionic emission, you have electrons, let's say, in a insulator or in a metal, and then you apply heat and you raise the temperature of that. So there'll be some electrons which will have to tunnel through a small, maybe narrow barrier, which might exist. Maybe there is an oxide layer on top of that and just penetrate the barrier. And so you will get this phenomenon of thermionic emission. Okay? So the more you heat, the more will be thermionic emission. I think this is governed by this Richardson law. I think it is Richardson who found this for the first time. But this is also a case of tunneling through a barrier. The other is, as I said, if you subject an atom to an electric field, then you have a potential like this. And in the simplest of cases, you can consider just a flat potential with a linearly varying potential due to the electric field, and some electron which is here in insulator, metal, whatever. Then it can tunnel through this barrier, and you can have electric field induced emission. So in fact, this led to, for instance, the field emission microscope and so on. You can actually picture atoms on the tip of a needle using that. And the theory for that, as I said, came about by these two gentlemen and by Oppenheimer. Yeah.
So the first figure, on the
Yeah.
other side of this metal.
Yeah.
it's like vacuum.
Yeah, this is, well, not vacuumness, it could be air. It's outside of the metal. Okay. So this is the zero. Okay. So the barrier could be due to you can have various sources of this barrier. As I said, an oxide layer will be a barrier. Okay, so this was the situation in the up to 28 or so, and this is also roughly the time when Gamow came up with his theory of alpha radioactivity, that it could be explained by tunneling. So, although alpha radioactivity was discovered by Marie Curie and Rutherford, roughly around 1900 or so, but the theory came much later for that. And of course, the mass spectrometry of Aston was necessary to establish that it was really tunneling was required. Because unless you know what is the energy release, you cannot say whether it's tunneling. Maybe it was above the barrier, maybe there was some other reason why it took a long time to decay. But once Aston, through his mass spectrometry, which was actually a great, he built these magnetic spectrographs where the accuracy of the masses of some of these elements could be measured to ppm level. Okay. So that enabled him to actually measure the Q value. Q values is just the energy release when A plus B goes to, let's say, C. So in this case, you want C to go to alpha plus something. So you have to know the mass of the daughter nucleus or the parent nucleus and the daughter nucleus, also the alpha particle mass. So if you know all of these to reasonable enough accuracy, then you can say that this is the energy released. And of course, by that time it was clear that the nucleus was a compact object because Rutherford had done these experiments in 1913, and then they got improved upon later and so on. And so we knew that the nucleus is a very compact object. We also knew about the strong force later, but that came later. But we knew that there is a barrier which is much larger for alpha decay than the energy released. So I'll come to that. There are a few slides after that. So this was necessary that you had a nucleus which was compact, and this was done by experiments which were the measurements for which were made on the suggestion of Rutherford by Geiger and Marsden. That is how things used to run in those days. There were technical people who would do the experiment at the instance of the professor. And the professor would come back and say, what have you done? And so on. And that's how. So the interpretation was all done by classical mechanics. It so turns out that in the Coulomb case, the quantum mechanical result, which was done much later, is the same as the classical result. But this was already enough for him to say that gold had a nucleus which was much more compact than the atom, more compact by a factor of at least a few hundred, of the order of a few thousand, in fact. And that came about because of the unexpectedly large event rate at large scattering angles. So you had to have large electric fields, and those large electric fields could only be possible if the nucleus is compact, not of the size of the atom, but much smaller. Okay, so the energetics of the alpha decay is as follows. For this to happen, you have to have this to be positive. That means Mb plus M alpha should be smaller than the mass of the decaying nucleus. And of course, the alpha carries away most of the energy. So it carries away, about 99% of the energy for heavy nuclei. For instance, if Q alpha is about 5 MeV and A is about 240, as the case, let's say, for plutonium or something like that, the daughter nucleus carries away only a small kinetic energy, the order of 100 keV. Now, the Coulomb barrier can be estimated to be of the order of 20 MeV, but the alpha particle energy is only 5 MeV. So how does it happen at all? So that is when I'll come to that again, some slides later. So the energy release, so this is just to get an overall picture of the present situation. I mean, present meaning around 2000. There's a nice tabulation or not a nice graph plotted in Hyde's textbook on nuclear physics. And you can see that the energy released, the alpha energy, which is mainly carried away with the alpha particle, versus A. So there are many nuclei which decay. For instance, you have these, plutonium and americium, and such like nuclei, fermium, all the way, and of course, thorium, uranium, which are naturally occurring. All these other nuclei have to be produced by a man, or they may exist for short whiles in supernova or something like that. And then there are these other nuclei, which are the in the chain of decay of the thorium and uranium isotopes. So things like actinium, francium, polonium, and so astatine, they are all products of this decay chain from starting from thorium 232, or uranium 238, or uranium 235. So you can see, as you go to heavier and heavier nuclei, generally speaking, the Q value increases. As you go to nuclei near the so-called doubly closed shell, lead 208 being the doubly closed shell, it has 82 protons and 126 neutrons. So there, the difference in energy between a non-closed, non-doubly closed nucleus and a doubly closed nucleus is quite large, and that's how you get the highest Q values of the order of 8.8 or so for polonium 212. And then, of course, it drops once you go to lighter elements. And in fact, even this is not shown here, but there are rare earth. Maybe it's there in the next slide. Let's see if it's there. Yeah, okay, alpha separation energies. There are alpha decays even in naturally occurring nuclei, such as the rare earth nuclei. So this is in this region. Okay? You can see this. Of course, the Q values are smaller. They are in the region of 3 to 4 MeV or so. And so this is the overall plot of the. So this is the binding energy of the last nucleon, and this is the binding energy per particle, which is about 8 MeV or so. So, and this is the alpha separation energy.
Right, the previous one, what
Yeah.
are those lines that?
Which one? Oh, these are just, I mean, you just join the dots. These are experimental points. So this is the Q value for polonium 212. Not all the nuclei are mentioned, but there's a range, host of nuclei for which Q values have been measured, which are alpha decaying spontaneously.
Why is there the downward trend?
No. So as I said, when you are just above the doubly closed shell, that's when you have the maximum difference. Okay, and then as you fill in those single particle states, then this energy comes down, and it comes down to a low of in thorium and uranium. And in fact, because it is low, that's why these guys have lived long enough. So uranium has a half-life of some, I don't know, 10 billion years or more than that. Uranium is about 4.5, I think it's 40 billion years. Uranium has a half-life of 4 billion, 4.5 billion.
I'm confused. So I thought if you go down here,
Yeah.
it is more unstable.
No. That's not. That's not.
So
See,
this is what energy.
No. So for instance, all these nuclei are, of course, unstable with respect to alpha emission. Many of them, francium, polonium, the lighter polonium, the heavier poloniums. This is, I think, actinium. This is astatine somewhere. Astatine, I think. So many of these nuclei, although they can decay by alpha emission, they also decay by beta. So sometimes it is that the beta decay branch is much more than the alpha. So they might be short-lived, very short-lived. And in fact, that is why you don't see them in significant quantities in nature, because they quickly decay.
So you're saying
So-
if the energy released is low,
Yeah,
it is more stable.
yeah, that's right. That's right. In general, that is true.
Why is that?
Because just so now we know the explanation that in a tunneling phenomena, as you bring down the energy, it has to cross a bigger barrier. And that's why it is long.
But this
Okay,
is
so the
energy-
typical, yeah.
This is the energy release though, right? I mean, it's not saying anything.
Yeah,
about the balance.
but this energy means that this is a positive energy. When you say that the alpha can decay spontaneously, it means that alpha has a positive energy. That's what is that energy at which it comes out.
So it's
So it has, so that is illustrated here. I think this will answer it. So the alpha energy is somewhere here inside the nucleus, and then it can tunnel through this barrier and come out with this Q alpha. That's the idea. And the higher this barrier or the wider this barrier, it will be more and more difficult for this tunneling to go through. And for most nuclei, this is true, unless you go to some exotic nuclei where the energy of the alpha is close to the barrier. Happens. Yeah. No. Q value can be determined experimentally. The accuracy is of the order of even sub KE. Yeah. Huh? How do you do that?
Theoretically, how do you compute?
Oh, theoretically. So theoretically, you have to model the nucleus. And typically, the best accuracies for so-called what? Liquid dropless shell can give you accuracies of the order of 200-300 keV. So theory cannot guide you better than that. Okay. So if you want to determine something, you better do it experimentally. That can give you, as I said, sub keV accuracy. Because in the early days, Aston used to do this mass spectrometry. You have an ion source, you give it, you accelerate it by a certain voltage, and then you have a magnetic dipole, you bend it, and that analyzes the momentum by charge. So if you have charge 1, then it is just the momentum, right? And by dispersing it enough in momentum space, you can actually get lines of this slit source line image. And that can be done with great accuracy, as I said, of the order of ppm. But now we have even methods which exceed that by several orders of magnitude. You can put these things in a trap, and that trap can measure, the cyclotron frequency of that charged ion to fantastic accuracy. I mean, it can be 1 part in 10 to the 12, 1 part in 10 to the 13. So as I said, you can actually find this out with keV or even sub keV accuracy in some. So it's nowhere near theory. Right? Theory is at least 2 to 3 orders of magnitude. So if you want to do this tunneling, and by the way, the tunneling, as we will see, depends very sensitively on the energy of the alpha particle. If you change that energy by 100 keV, the rate of decay will either increase by an order of magnitude or decrease by an order of magnitude, maybe on 2 orders. So it is very sensitive. So what is done is you actually use experimental values for the energy or ground state energy. So what is that? Parent and daughter, and of course, alpha particle mass. And then you use this in your whatever phenomenological model you have, calculate the rate. And we'll come to that, what it actually tells us. What do we learn from this decay? Pardon?
Gradient
Yeah.
constant for
No, this is just a schematic of a alpha nucleus potential. It will depend, of course, on what nucleus you consider. And I mean, there might be corrections to this simple-minded nuclear potential plus Coulomb potential. Because there might be, effects like polarization of the nucleus, polarization of the alpha. There will be higher order effects. But grossly, this is the way the potential looks like. This is just to illustrate that something has to tunnel through, and that tunneling probability can be calculated into various degrees of source. But there are still lots of other uncertainties which I will cover. So, in principle, these phenomenological models cannot predict the decay rate, sometimes even to factors of 2. So you actually try to use data and some phenomenology, and then you will try to extract some parameters of which might be relevant to the model. Sorry. Yeah. Sorry. You had a question.
No, I was saying that the points where the dotted line is cutting,
Yeah.
if I keep those 2 points fixed and increase the height,
Yes.
then also probability decreases.
Will decrease. Yes. Sure. Absolutely.
Although Q alpha did not change.
Huh?
By doing that, Q alpha did not change.
QL.
Yeah, it's the same height, but
Yeah. He's saying the energy is the same, but I increase the value. I mean, this is what you can play with. In real life, of course, if you want to increase the value, you have to also increase the nuclear size. Or, you have to put in much more protons, maybe that's not possible. The nucleus will decay by proton, whatever. So,
yeah, I think theoretically speaking, the kinetic energy of the instanton is increasing when you increase height
the kinetic energy.
of the instanton. If you go to the Euclidean time,
Yeah.
there is a classical solution
Yeah.
in the forbidden region.
Yes.
That particles.
No, so it will,
kinetic energy is
if this
increasing.
height is larger, I guess you will also have to increase the width normally.
No, if you keep those fixed.
Oh, keep that
then
fixed. Okay.
Then
Okay,
the
just
kinetic
increase the height
energy,
arbitrarily.
then the kinetic energy of the Euclidean solution is increasing. And that gives
You mean
more
in this
suppression.
region?
Yeah.
The imaginary energy.
Yeah.
Yeah,
That gives
sure.
more suppression.
Yeah. That's right.
Sorry, one thing, I'm not sure if this is a fair question, but on the left also you think of the alpha as.
So that is where these details become important. Now, if you can't, an alpha is not a neutron or proton.
Right.
When a neutron or proton exists as a neutron proton, presumably, maybe it's a dress particle, but essentially it is the same.
Right.
Maybe there is a ion cloud, maybe there is some, quark antiquark pair. But is it like that? Can an alpha particle exist deep inside the nucleus? Probably not, because there are other nucleons with which it will collide, and you can make off-shell transitions. So it may not survive. On the other hand, on the surface of the nucleus, it is more likely that such cluster states might exist for a longer period of time. So what these theories will try to do is to extract the so-called cluster probability, and also they will have some, other parameter, which is how often can it, hit the barrier. That depends on the kind of barrier that you choose. So there is some modeling involved, which there will be some gray area in that.
Do you have to count how many clusters are possible in a given nucleus and then multiply the probability by that?
Yeah. But you see, the clusters that in any theory that you take, in any nuclear model, the clusters will come from the particles near the Fermi surface. So the last two protons, among the few protons that are there near the Fermi surface, and the neutrons near the Fermi surface, they will sometimes combine to give you an alpha, and they are more likely to
count.
For
a given nucleus that can be counted. How many clusters?
You can, and so you have to model it, and so people have made models now.
Work or those work?
As I said, you can do things right to within about a factor of 2. You can't believe it. There are people,
So
of course,
for larger nuclei, the statistical models work quite well. For larger nuclei,
yeah.
the statistical models work quite
No, so statistical model works when you are considering, let's say, decay, a comparison between the decay of various channels. So suppose I can decay by a photon, I can decay by a proton emission, I can decay by a neutron emission. There I can make a reasonably good comparison through statistical models. And that in fact was first done by Niels Bohr, and then people did things in more sophistication. So there, but if you consider alpha emission, then there is the same problem. How can you predict how much alpha emission? Because I have to know the cluster probability, and so that's a problem.
In the case of beta decay, it is argued that electron cannot exist inside the nucleus.
What is that? What cannot exist?
In case of beta decay,
Yeah.
electron that is coming out
Yeah.
inside the nucleus because of the uncertainty.
Yeah, but that comes about because the electron is very light. So if you calculate the uncertainty in the energy, that comes out to be very large. So there has to be some other unknown interaction. But that if there is some unknown interaction, it should have been possible to see it in scattering experiments. So then we don't see that. So there is, as far as we can tell, no other interaction other than electromagnetic when it comes to electron interacting. Right? So that's the argument. But in the case of alpha, the mass is much larger. So if you calculate from the uncertainty principle, you'll say it's possible. Why not? Because it goes inversely, right, to the mass. So it's possible. Okay, so this is what I said, so I'll not repeat myself here. So these are the papers that Gamma wrote in 28 in Site Physics. And these people wrote this paper in 28 in Nature at a very similar time. In fact, they didn't know, I think, of the work of Gamma. But in the later work, of course, they knew. By then, they knew Gamma's work and they mentioned it. And this was a more detailed paper, in fact, looking at various potentials and so on, and trying to infer how the probability changes and so on. So this is, of course, Gamma, and this is Condon. If you actually solve for eigenstates of the alpha in a nucleus, these positive energy states will not be strictly stationary, and there will be that is due to quantum tunneling. So the wave function will decay in time, and that is put by hand by putting a small imaginary part in the energy of the alpha particle. So of course, if you take the square of this psi star, then you will get a factor that depends on the energy e to the minus gamma by t. Gamma would be the width for such a decay.
Sorry, just to go back.
Yeah.
This comment about beta decay. So
Yeah.
that is then not viewed as a tunneling phenomenon.
Beta decay.
So the thing saying that the electron does not exist inside by the uncertainty. So
No. So if you calculate, suppose the electron were confined
Right.
originally to the nucleus,
I think it will be
then the uncertainty in size is so small
that's right.
and the energy is very high.
That's
So you would need some other interaction to bind it.
all that is true. Yeah. So
Yeah.
you will not view that as a tunneling phenomenon,
Yeah.
but something else.
Yeah.
Whereas
I mean,
here
maybe you could say that, okay, is it possible that there is another interaction which brings down that energy?
Yeah.
Possible.
Okay.
And then that might lead to this tunneling.
It seems like a bit
Although
of
it will be
money.
better, I think there the equation will be slightly different because the potential is always attractive for the E minus.
Yeah.
It will always be attractive. There is no such thing as a,
So once electron is produced.
once it is bound, it will remain bound. Yeah.
Once electron is produced.
Yeah.
You need tunneling to come out, for it to come out. You
Yeah.
don't need tunneling. for it to
Yeah.
come out.
There's no
So,
barrier.
because there is no barrier, it is going to zero at large distances. And maybe there will be a polarization potential or something like that. at large distances.
So it has to be viewed as very different.
Yeah.
Things for them.
That's okay. Okay, so now, I mean, intuitively, we can see that if such a thing were to happen, then as the Q alpha increases, the width of this state will increase because it will have increasing chances of leaking out from this. This, even without solving the problem, you can intuitively feel, right? Because now the wave function has to exist here and here, and there is a better overlap if it is higher up in energy and smaller overlap if it is lower in energy. Okay. So this is what you expect. So the approximate way, yeah.
The change is by going to different nuclei.
Yeah, so if there is a state, a quasi-stationary state in some ordinary nuclei, where the Q value is higher, you will expect a larger decay rate.
Yeah.
That's because, and therefore that width of the state will be larger. That's the
And that is seen.
Huh? That is seen, yeah. And in fact, did I have the, no, I only had the separation energy. I think we'll come to that. There is something called the Geiger-Nuttall plot. I hope I have a slide on that. So basically it is the log of the half-life related to the Q value. Of course, there are different bands because it depends on which region of the isotopic table you are. But if you are looking at similar Z region, then as the Q alpha increases, the half-life decreases dramatically. That's the idea. Okay, so you can do this, as I said, in increasing sophistication. And for instance, you can first say that, oh, I want to do this in the simplest possible way. So I just penetrate through a rectangular barrier. Not a good approximation, but to get some idea of, the Q alpha dependence, maybe it is not too bad to get a feel. Then you can put an attractive well of constant depth, a square kind of depth, and up to some R, and then a constant rectangular barrier. That's what it is. And then, of course, you can put a realistic alpha nucleus potential and the tunneling through that barrier. So, again, I will not go through this in any detail, but basically it involves solving a one-dimensional barrier penetration problem, where you have a barrier like this, you have an energy here, this is the zero, and so this guy tunnels through this barrier. This is the simplest way you can do it. Basically, the leaking part of the wave function is governed by this e to the minus g. G is known as the gamma factor, and that depends on the square root of the difference in energy here between the barrier and its energy. So V minus E, that is what comes here. And then also it depends on the width of the barrier. This is B minus A. And this is all in the exponential. So things change dramatically if you change one or the other factor.
So that is the kinetic energy I was referring to.
Yeah. Inside the barrier. That's right. Okay, so this is a more realistic potential, where slightly more realistic, I would say, because of course this is a steep rise here. In fact, there will be a Fermi function dependence here. Okay, so again, I will just mention that you have to solve this in these three regions: inside the well, in the barrier region, and so you have to basically match these wave functions, and you will see that the wave function in the barrier region decays exponentially. And the factors which dictate this exponential decrease are given by these Q values and thickness of the barrier and so on. So I'll skip this.
This is also WKB, right?
Yeah, this is a W. So the decay constant can be expressed as a barrier penetration probability times a barrier assault frequency. And if you take a log on both sides, then you can see that log of the T half is inversely proportional to the Q alpha. So as Q alpha increases, the log T half decreases. And this is also known as the so-called Geiger-Nuttall law, which was found empirically by Geiger and Nuttall. This, I don't have the references here, but must be one of these philosophical magazines or nature of that time.
That barrier assault thing is how high it is.
Because after all, when you have a time, you have to have another time scale. So that time scale you can interpret as the assault frequency, which is basically
How high?
it is inversely proportional to the velocity of that alpha particle in the well and the dimension. So D by V essentially is that is the assault.
So one has this energy and the other one is a barrier.
Yeah.
Height above that.
Yeah.
So it's okay, two times.
So the time scale is decided by this because you have to have something to scale time. So that is the time scale. And then of course it depends on that exponential factor, which depends both on the difference in barrier height and the energy and on the width of that. The so-called classical width. Okay, so this is the Geiger-Nuttall law, basically which shows these loci of the points for various nuclei, right from californium, which is one of the heavy nuclei which can be produced in a reactor, to very light elements like I think this is erbium or something like that. So as the as you go lower in Q value, so for instance thorium and so on, they are of the order of 3.5 to 4 MeV. The half-lives are the largest, and that is why they have survived to this day, 4.5 million years. Earth's lifetime is of that order. Right down to something like nanoseconds, or 10 nanosecond or so in some of these very heavy nuclei. I don't remember what is this symbol. This symbol represents EM. Maybe it's Einsteinium. So it's a nucleus which is heavier than californium.
Nothing tells you in advance whether it's alpha, beta, or not.
Pardon?
This is only for alpha.
It's only for alpha. Correct.
So it would,
Oh yeah, some of these nuclei could alternatively decay. As I said in the earlier slide, many of these nuclei are actually decaying faster by beta decay. So although beta decay is a much slower process than a strong process, but in some cases, because this is hindered, that one might take over. That happens. In fact, many of these nuclei in the uranium thorium chain actually decay by alpha, then decay by a couple of betas, and then again decay by alpha. So there is a path of this sort which occurs. Okay, so this is the general trend, and this was empirically found, as I said, by Geiger-Nuttall. When they, at that time, maybe they had 1/10 of these nuclei, the number of nuclei. Now we know many more. Incidentally, we know of the existence of about 3,000 nuclei, and models of nuclei in general predict that there should be about 8,000 nuclei. I should define, of course, what do you mean by 8,000 nuclei? These nuclei are the ones which have separation energies or which require a certain energy to be given to the last neutron or proton to come out of the nucleus. So, because there are also nuclei which have, because of this barrier or L barrier, maybe Coulomb barrier, things which can be positive energy, not such things which are bound. Separation energy is positive, or the binding energy is positive.
So can there be something where it is like a resonance thing? Which
Yeah, those things anyway. So when you say that there are 8,000 nuclei, maybe there will be 12,000 nuclei if you were to consider resonance states. That number will be then much larger.
So, but then
These are 8,000 stable, nuclei which are stable on the strong interaction time scale and which cannot spontaneously emit protons and neutrons because their separation energies are negative. So that means the binding energy is negative.
you cannot spontaneous. Which means they are
you're not considering those nuclei, only those nuclei where binding energy is positive. It may be small, maybe 100 K. There are indeed such cases.
Is that saying that they are stable?
Yeah, so we call those stable nuclei. Stable, as I said, it's a relative thing after all, because all the time, strong interaction types.
Are there observational cases where
Yeah.
WKB doesn't work?
Where?
WKB doesn't work.
Ah,
Not only in this, in any situation.
I see these are, I mean, again, on the scale of the time scale of strong interaction, these are actually very slow decays anyway. So I think this so-called approximation where you have a
What they do-
potential which is being faced by the particles and getting emitted, I think that's not too bad enough. So WKB is okay.
If-
I don't know. I mean, maybe if you have some other approximation, maybe it might do something slightly different. But I
No,
think
not
the
slightly
nuclear
different.
models are not, so sharp that you can distinguish between these two. Because the nuclear models have, as I said, you have a factor of 2 uncertainty from your nuclear process, so you can't distinguish it.
So this 8,000 are things in the periodic table and their isotopes.
Yeah, no, we don't know. We think that there should be 8,000 nuclei, but we have actually found 3,000 nuclei. About 40% of them we have found.
That is the
Sometimes it
periodic
may
table.
be just that I have one such nucleus or a few such atoms
Yeah.
based on detection in a mass spectrometer, we call it mass spectrometer. Some of them, a much smaller number, maybe half of them, we know about the spin parity of those states and maybe even a few excited states. So where spectroscopy is known, I think that would be, so there are about 300 stable isotopes on Earth. Maybe about 5 times that number we would have good spectroscopic information.
Sorry, if there's
And about 10 times of those nuclei, with the other nuclei, we have very sparse information. So there's a lot of work that the nuclear physics community can do.
so they are
That's why you need accelerators and you need good detectors and so on.
not absolutely stable and therefore we don't find them.
Yeah, and they have to be, I mean, they might be created in places like supernovas or some of these great events that take place in the cosmos, but we don't see them so easily.
Because they decay.
Yeah, because they decay. And also, even if they are produced in supernova, you will only see some of those decays because after all, they have to reach great distances, right? So they may not reach you. And especially if they are short lived, by the time the dust settles down, you will not see them. So you have to create them in the lab. So that is what the so-called radioactive ion beam facilities are doing. They actually make radioactive ions, which are very much off the shell, and then study their properties. So that's a big business. Okay, so now I come to some additional points and maybe some refinements. So first of all, you have to know what is the formation probability, and this itself is a big problem because it involves clustering of 4 nucleons, and probably that happens on the surface. Also, it would depend on the single particle orbitals that are involved, which will make that alpha particle in the first place. Then there is also the effect. This is a minor effect, and this can be, in principle, calculated. That if you have a angular momentum of the emitted alpha particle, then of course the barrier changes slightly because there is a so-called centrifugal barrier, basically something proportional to L into L plus 1 by R squared, and of course the reduced mass. But that is something that slightly increases the width if you are dealing with the large orbital angular momentum. And then there was, as I said, nuclear structure effects because the light nuclei have more surface to volume ratio. So they can have more clustering. You might say that the lightest of nuclei have all surface. So they will have more clustering. Whereas heavy nuclei in the interior, even if alpha is there, it will dissolve quickly. Whereas on the surface is what counts. So for instance, you can, okay, this is again a calculation. The reduced alpha widths for even polonium isotopes. So you can see near the shell region, this goes down, doubly closed shell region. This is not doubly closed, it's singly closed. So this reduced alpha width, which is to say what is the probability for this alpha cluster to exist, is dips. And then again, it increases when you go to higher mass numbers because then there are more states of neutrons near the Fermi sea. And of course, alphas, polonium has 2 protons more than the lead. They are anyway there. So you can combine them with neutrons to form alpha particles. So there are these effects which lead to changes. For instance, if you have a finite L, then it increases the barrier ever so slightly. But even this small increase in the barrier width can have quite spectacular effects in the lifetime. For instance, from L equal to 0, S wave, to L equal to 4, okay, which is FG, G wave. It decreases the probability by almost a factor of 30. So the penetrability decreases, even though this you might think is not that important. And this can be estimated for such a nucleus. Okay, now is alpha particle decay the only spontaneous decay that occurs from some of these nuclei? No. Indeed, it can be shown that there are other forms of decay, except that since the barrier, yeah.
Sorry, is there any other way of computing other than clustering, or is that the?
I mean, see, if it emits 2 protons and 2 neutrons,
Yeah.
whereas free particles, you don't gain that 28 MeV energy.
No,
2
even
protons
if
and
it is alpha,
ah,
but something directly, because quantum mechanically, all I know is in the final state there is an alpha.
there is an alpha. Yeah.
I don't want to presuppose that there is an alpha.
Yeah, so I don't know if there are some models which say that these proton and neutrons can penetrate the barrier and somewhere along the way they combine.
That's-
And then they give up that energy to the
That's
daughter.
Yeah,
I don't think
That's a more
there are-
direct way of.
yeah, so no. Yeah,
There was a computation.
I mean, you have to think of a mechanism whereby they combine to, by the way, alpha particle binding energy is close to the typical nucleon binding energy. Typical nucleon binding energy we learn is about 8 MeV per nucleon. And in the alpha particle, it is 7 MeV, 28 MeV, very tightly bound system. So that is why people tend to use this approach. That anyway, it's a very tightly bound system. So maybe it is formed and these are reasonably successful. As I said, these are a factor of 2. Some people claim even 50%, better than 50%. But anyway, that's the kind of accuracy that people have. Okay, so just as you can have alpha emission, you can also have heavier cluster emission. And the first such case was actually found by Rose and Jones in a Nature paper in 80, which they reported in Nature in 84. So that's almost 40 years, very, quite a few years back, right? And so, of course, that decays by 225 actinium, certainly decays by alpha emission. So this is the helium-4. And you see this carbon-14, and there's just a couple of counts here. Okay? And that is something like 10 to the 6. So it's a very small branch. And by the way, I don't have a slide for that, but people have even seen, for instance, magnesium-24 coming out spontaneously from some of these nuclei. 28 silicon, I think that's the heaviest that they have won in terms of light nuclear emission. And so the problem, why it is so small, is that it faces a much larger barrier. Because this goes like Z. So alpha has 2, Z equal to 2, this fellow has Z equal to 6. And if you take silicon, it has Z equal to 14. So these barriers are much higher. So if you have to penetrate the barrier, there is much less problem. So that's why it's very rare. But anyway, people have done these experiments, and these experiments, particularly the first one, I think was done with some of these sheets which are exposed to, I think, either photographic film or these emulsions. And then it produces a track which you then put in an acid, and the track becomes visible. So you look at it under a microscope and you get the right Q value which is expected and so on. And that's how they measured this decay for the first time. Of course, this particular measurement was not done like that. It was done with a solenoidal superconducting spectrometer. So it transports these decay products onto a focal plane. So the solenoid is just a coil of superconducting wire, and the source is at one end of the solenoid. So these particles come out in all directions, but it sees a very strong magnetic field because of the superconducting nature of the coil, and it's a high field. And so those that come out in a certain range of angles, they actually make helical paths, and then at the other end of that you put a detector and you count them. So you can put gas and you can put so-called delta E telescope. You can identify these particles. You can distinguish between alphas and energetics also, of course, is in principle enough to distinguish it because this is a much higher Q value. So in this case, for instance, the Solno measurement in France, they could measure the partial half-life with a 30% accuracy. Of course, this measurement is, by the way, with a track detector, but they did this with a solid state detector. So I don't have that measurement. This is this Uran et al. 1991. I don't have that number, but that agrees more or less. There's a question.
Yeah. So this protein C that's emitted.
Yeah.
It's like literally uncharged all. So it's got what 7 protons and 7 neutrons.
No, 6 protons and 8 neutrons. So carbon 14, this is the same nucleus which is used for dating.
Yeah, it's in nucleus that's.
But that decays on a very long time scale, 5,000 odd years. So
Right.
on this time scale,
Right.
it's like living forever.
Right, okay, fine.
Sorry, generically, these are all can be thought of as fission.
Huh?
Fission.
You might say very asymmetric fission, possible. Yeah, that's possible.
Even alpha emission
There
is
is in
some
fact-
special case of a fission.
Yeah, you can think of it in a generalized way. Anything that breaks up, you can call it fission. Yeah.
But
So there are some people
in terms
who
of
prefer
the
to use
theory-
that term.
in terms of theory, that's not a useful way of looking at it.
Well, I mean, not that it's not useful because after all, you have to talk about penetration through a barrier. It's simpler in the case of alpha. When you talk about heavier nuclei which are fissioning, I mean, then it becomes very complicated because those daughter products have perhaps a non-spherical shape and there are so many of them. They have excited, low-lying excited state, so it becomes extremely messy.
So they are not
No.
analyzed the tunneling.
No, so that is much more difficult to analyze. So this is much simpler. So you
But
can
we-
call it fission if you like. If you don't like the
We
word
have a,
for tunneling, you can call it a very asymmetric fission.
so we have a theory for symmetric fission also in
Yeah,
terms
yeah,
of tunneling.
So I'll come to that. So in this sequence, I just mentioned 24 magnesium and 28 silicon decay, but I don't have pictures for that. But I will go to the simpler case first and then go to the fission case. So for instance, you can, just as you have alpha emission, you can also have spontaneous proton emission. So you can make nuclei where the proton energy is actually positive. And now it will face a barrier because strong plus Coulomb, then there will be a barrier, just like in the case of alpha. Except that here, I mean, you can much better approximate the single particle strength because you have reasonably good models. Okay, so mean field models are there which will tell you. So in spite of the fact that there will be correlation, the quarter correlation, very good. But still you can get a reasonable idea about the single particle strength of the proton that is getting emitted. There might be a mixture also because of these other interactions, but still you are in much better shape here as compared to cluster emission, like the alpha, simplest cluster, the alpha. Oh, by the way, I should also mention that there are also cases where you can have triton, helium-3, even deuteron emission. I will come to another case where there is two proton emission. But proton emission is relatively simple and it was discovered again long time back.
Sorry,
First from isomeric states in cobalt, but now there are, I think this is also a bit dated. I think there are now about 60 or 70 such spontaneous.
sorry, so very basic question. So
Yeah.
why is helium like alpha particle preferred
Yeah.
over a proton emission in that same?
Why is alpha preferred?
Yeah.
No, there's no question of preference. This was just historically seen for the first time.
So the alpha emission has a higher rate compared to proton emission.
No. Rate completely depends on what system you're on. That
No,
depends.
if you take a particular system which
Uh-huh.
emits alpha,
Yeah.
why in that system does it not emit a proton?
Because of the Q value. The Q value might very well be negative. Just energetics doesn't allow that proton. For instance, take a
Because of the binding
typical
energy.
even radioactive nucleus, even which beta decays by beta plus emission. The proton is still bound. It's only making a transition to another neutron state, which happens to be lower in energy. That's all. But both of them are bound.
But if it is
So it
alpha,
cannot spontaneously emit a proton.
because if alpha, it is a binding energy that allows you to.
Yeah, so if you have a negative binding energy, then you can have emission. And there are cases now that are, I mean, now meaning what? It's almost 54 years old, right? When it was first discovered. So for that, you have to make proton-rich nuclei. That can only be done in accelerator.
So then why not something more strongly bound than alpha? Why isn't that preferred as a decay?
That's what I said. If you go to heavier nuclei, where maybe the average binding energy might be 8 MeV. But if you go, let's say, silicon, or even carbon 12, the barrier will be much higher. So, I mean, see,
Oh, yeah.
it is possible that there might be radioactive nuclei which you can produce using all the facilities that are there. But that decay branch will be very small as come. So if you produce these fellows in the first place in small numbers, if you have to study a decay, I mean a decay branch which is 10 to the minus 8, you don't have enough nucleus.
So it's a competition between.
Yeah, that's right. So in this case, for instance, I'll show an example. So, for instance, you can here the structure part is in reasonable control. So now you have a single particle state where it is supposed to be decaying from. Now you might not know in these very proton-rich nuclei what the L value is for that single particle state, and you can actually do calculations for L equal to 0, 2, 3, 4, 5, and then from experiment you know the Q value because that is an experimental measurement. And from the half-life, you can tell that this matches L equal to 5. So you can say that this proton comes from the L equal to 5 single particle orbit. You can fix it this way. And similarly, 2 proton decay has been found. And in this case, yeah. I think this is the 3 slides, I think. There's 26, no, I think I have 29 or 30. So, yeah. So maybe I'll skip over this. This is a case where this proton-rich nucleus, iron has 26 protons, and therefore this has only 19 neutrons. And I think people have made even further neutron-deficient nuclei. In this case, for instance, they use a recoil or a magnet, dipole magnet, to look at this nucleus, and then it enters a gas counter where you look at some scintillation in coincidence with the 2 protons, and you fix it properly. Then you can take the angular distribution of these protons.
So because it has such few neutrons, it wants to get rid of these protons.
Yeah, so it is so proton rich that these 2 protons are. Now you can ask the question whether this, when you say 2 protons, are they in a sort of resonance or 2 protons near 0 energy, or is it that this is a 2-step process? So it turns out that in this particular case, it is a 2-step process. But there are other cases in which we think that it went through that 2 proton quasi resonance and 2 protons came out simultaneously. So anyway, this is one example of that, but now many more examples of this are known. Anyway, so on the other hand, spontaneous neutron emission has not been seen. I actually tried to look for possible cases. I couldn't find any, but maybe in future, the best case seems to be 25 oxygen. Oxygen, you might recall, has 8 protons. And so this fellow has 17 neutrons. So this has so many neutrons that the last neutron might well be a positive energy. And it goes into a D wave, and it would have, decay energy, which is very small. So it would be difficult to see it. Pardon?
There are so many neutrons in this to beta decay.
Yeah, so that is exactly the way it decays. So we have not seen spontaneous neutron emission. That would be interesting to see, but we don't have. Just as in the case of proton emitters, we have many of them. I think something like at least 20, 30 of them. But in this case, we don't have. So the first one to be found, I think, will make news in Nature or some place.
So this one would not be a barrier.
Huh?
It's not
No,
a barrier.
so the neutron S wave doesn't have a barrier. That's true. Oh, okay. But if you have L, so that in fact that is the reason probably why it doesn't exist. You have to go to really neutron-rich nuclei, and you have to be in some orbital which has a relatively large L, so that it can survive. Because to find this, you usually make it pass through some electromagnetic filter, okay, some E cross B or just B set of dipoles, whatever. So it has to live for on the order of 100 nanoseconds. That's a pretty long half-life. So you have to have a thick enough barrier or a low enough energy in order to see it. That's probably the reason why nothing like this has been seen. But someday, I'm sure it will be seen. Okay, then I come to the spontaneous fission decay. So this, of course, was found by Hahn and the experiments, carried out by Hahn and Strassman, basically chemistry experiments, but which were inspired by Meitner. I mean, she had this program of transuranic elements study of that. And in fact, when they found this krypton and barium in the products, when they irradiated uranium with neutrons, they couldn't interpret it. So Meitner told them to go back and do the chemistry once again. They did it, and she was very confident of the, expertise of Hahn. So she said, therefore, okay, then this result is correct. And that's how, within a few days, Frisch, who was visiting on a walk, she just said, yeah, I think this is the fission. The nucleus is splitting apart. Something which most physicists thought could not happen. Because you are actually radiating with the thermal neutron, very low energy neutron, electron volt neutron. And then suddenly, this is a dramatic event in which 200 MeV is emitted. So this is a real surprise. And of course, the theory was worked out by Bohr and Wheeler. And Bohr is supposed to have said that, this is something that, we are all fools not to kind of hypothesize this immediately after. But it was Meitner who did it. She knew enough of nuclear physics to be that. That was a great insight. And then, of course, Bohr and Wheeler wrote up the theory. It's actually one of the seminal papers in the area of nuclear fission. Spontaneous fission was also discovered by Fleroff and co-worker in 1941 from uranium-238. However, a year earlier, Chatterjee at the Bose Institute and Chatterjee and some colleagues had observed this evidence in looking at emulsions or plastics which were irradiated with this and then developed. And they sent this paper to Science and Culture. But the director of that institute, who was, I think, either the nephew or something of the great Bose, Jagdish Chandra Bose, he objected to this and said that you have to withdraw this paper. It didn't go through him. So anything that went out of the lab had to go through him. And so apparently he asked them to withdraw the paper. And so they actually lost their claim of making this discovery.
Why did he ask them?
I don't know. I don't know. But this has been mentioned in literature. In fact, this D.K. Srivastava has written, I think, either in Physics News or some other place. And so, anyway, although they made the discovery, they don't get the credit for it. And Fleroff, of course, he was a very famous guy in those days. The next important discovery in fission came in 1962 when Polykonov, irradiating various heavy targets in beams at JSI, found that there are isomeric states with very short half-lives. Okay. And this required the understanding in terms of a combination of the liquid drop and shell effect. And that was done by Strutinsky, and a little earlier this was hinted by Myers and Swiatek. So this led to a better understanding of this combined effect, where heavy nuclei were supposed to show liquid drop behavior, but on the other hand, we know that the shell model, the mean field model also worked. So this was combined by Strutinsky to find that this can lead to, for instance, potential energy versus deformation curves, which have a second minimum. And so this Polykonov discovery was of a nucleus where the nucleus was existing somewhere here, because then it had to face a very small barrier. If you have a nucleus here, it has to face two barriers. So the tunneling probability decreases. Whereas this half-life was as low as 14 milliseconds. And either in the same nucleus or in some other nucleus, which showed also such isomers, Van den Bosch found a gamma ray decay from these states to this state. And much later, another maybe 20 years later, in Heidelberg, there was even spectroscopy done on these so-called second well states. So these, because they have large deformations, they lead to moment of inertia which are large. So these states are actually rotational states built on the ground state here, corresponding to the second well. So conversion electron spectroscopy and many other spectroscopic properties were studied as a result of this, and they confirmed this idea that indeed you can have splitting of barrier. Of course, there might be also situations where you can split it into three barriers. Those are basically, the idea is that you can split a barrier from just being a single barrier to two barriers with a second well minimum.
Sorry,
These are big advances. Yeah.
So the neutron puts that thing in the next
No. So the Polykonov experiment was done with heavy ions. So you actually populate states both in this well as well as in that well. But you see if you populate these states, they will take a much longer time to fission. They will fission on the scale of seconds or maybe days. Whereas this one was a very short-lived state, and they could identify this.
So for neutron induced fission,
neutron induced.
is it like
In principle, you can also populate this state. So not necessarily through thermal neutrons, so you can do that with some component. But people have done, for instance, DP reaction. So you can transfer a neutron and get to some of these states.
But
No, they are higher energy, right?
was the simple fission that is not the neutron induced fission?
No.
That's
Thermal
not-
neutron induced doesn't populate these
So it's
states.
just like a Canadian.
Because see, this difference in energy could be as much as 2 to 3 MeV, maybe even more. So
So there, what is the thing? It is only.
in uranium 236, for instance, there is, as far as I know, there is only one barrier.
Okay.
So
So there it is.
it has to penetrate one barrier.
Kinetic energy transfer from the neutron.
No.
So is there a neutron
nucleus that is
captured?
formed is a compound nucleus, and then that spontaneously, I mean, that evolves in time
Okay.
and it fissions. So it's like alpha decay,
Okay.
but it's a more symmetric form of decay.
So that is also by turn.
So alpha decay, as you said, can also be considered as fission, but very asymmetric, highly asymmetric.
So this is
This is
also-
more symmetric fission.
Once a neutron is captured, then it is the tunneling.
Yeah, then the fission fragments are tunneling.
Okay.
But it's a much more complicated process because each of these has large number of degrees of freedom, large excitation. So
So
it's
the liquid
very
component.
complicated. Yeah.
And what is
Okay.
the pink point there? That was.
Huh?
There was some pink.
Which one?
Is-
Oh, this is the so-called, this is just to, some of these models say that, okay, there is a point where these two fragments are just touching one another. That's called the scission. Just to illustrate where that scission point. Because you can see that that is right at the large deformation, very large. So that is when it just splits before it parts ways. Okay, then I just have one slide on this. Just as you can have spontaneous decay, you can also have fusion reaction. So I give a couple of examples of such a process. You can have DT fusion, for instance. This is the reaction that is being sought after by people who want to produce fusion energy. In, for instance, that experiment in France, they want to make a reactor out of it, producing electricity. So the basic idea is that if you increase the neutron energy, there is a peak in the cross section at the order of 100 keV. So this is not, of course, done by accelerating particles. It is by heating a plasma, tokamak. But the idea is that you DT fuses to give you a reaction in which you have a neutron and an alpha particle. Similarly, you can have fusion reactions of DD. This cross section is much lower. So although D is much easier to handle than tritium, but then the cross section is also that much lower. So you can see that at low energies, this cross section is differing by 2 to 3 orders of magnitude. So, of course, this is the preferred reaction. And then, of course, you can take this to very heavy target and projectile. For instance, here you have if you increase the energy as compared to the barrier, then the cross section steeply increases because the penetrability increases dramatically. And then it, of course, saturates when you are near or above the barrier. So this is when this is the barrier, one, E by B. No, this is some other, this is for, okay, argon plus T. These are for some other things. So this is the general behavior of heavy ion reactions for giving rise to the fusion reaction.
So there is some connection
Oops.
between.
This is the last slide.
There is some connection between cross section and barrier, right?
Yeah,
Or are they
because this is just the inverse process, no?
Okay.
In order to make a fusion reaction, it has to tunnel through this barrier if you are at energies which are lower than the barrier.
Okay.
So that is how the
So higher cross section means what? Like-
higher cross section means you have gone up in energy higher, so you are closer to the top of the barrier.
So lower barrier.
Yeah. So even for instance, if you are above the barrier, you don't get the full cross section because there is also a reflection probability, right? Even from the one-dimensional model, you can say that. So it leads to some reduction in the cross section that you would expect. Semi-classical, you can say. But you can understand these things in terms of basically tunneling. Except that, I mean, the one-dimensional tunneling may not be enough. You have to couple other channels that might excite states in the target and projectile on the way. And so instead of one barrier, that one-dimensional barrier has to be split in many barriers. And of course, when you split the barrier, it becomes easy to penetrate a lower barrier. So you can have dramatic results on the fusion. That's how you get this so-called sub-barrier enhancement. So this is what a one-dimensional static barrier would give you. But you have a cross section, especially at the lower energies, which is several orders of magnitude higher. That's because it is believed that this barrier splits and then you can have a large effect on the tunneling problem. Because the higher ones anyway don't give you much problem, but the lower barriers give you a big jump in the tunneling. Yeah, okay, so I think I just like it. And we have already been questioned. So.
There are any more questions?
I exceeded my time by quite a bit.
No, yes. Vivek's
So tomorrow-
next call will be tomorrow at 11:15. Sorry, I'm shuffling and reshuffling, but I think.
So maybe on the website or something.
Yeah,
like that.
it's on the-
But also I want to change the title on the last stop. Two slit interference. That's what.